Hi, welcome to day 9 of the 100 Days of Common Lisp series. So, if you notice, it's been a while since I posted the last video because I was actually planning to follow the original series and actually cover things like A list, P list in this slot, but then I just kept procrastinating on it because it was boring. Now I finally decided to kind of completely do something different of our own. So we're not going to do this. We are going to do something interesting. So instead, we are going to try to draw this diagram, the Mandelbrot set, a fractal from Common Lisp. So I want you to take a few seconds to kind of pause and think about how you'd approach this problem, if not in Common Lisp, in any other language, and then you can kind of continue. So there are two aspects here to be able to do this. One is you need to kind of have the logic on how to draw the Mandelbrot set. That I'm just going to lift from Wikipedia. I'll show you in a moment. And second, we need a way to actually draw things, right? As in not just uh, the algorithm, but also the actual drawing capability. How do you write it? How do you draw pixels onto PNG or something? So for the drawing part, I am going to go with Cairo. If you heard of this is the very common 2D graphics library. So it has functions to draw and things like that, and also different outputs. So you can draw to a PNG or an SVG or an X11 window and so on, right? So we are going to do, I mean, it has a very complex drawing model with multiple colors and masks and so on. I don't know a lot of this myself, but we don't need all of that. We need a very simple version of it because we are going to draw things one pixel at a time, right? Of course, you could do more complicated things, but for this problem of drawing fractals, I'm going to just break it down into pixel by pixel, and we'll just draw one pixel at a time. But how do I do that from Common Lisp? So luckily for us, we have bindings. So this is known as CL Cairo 2. So we are going to use these Common Lisp bindings to be able to do this drawing, right? And there is also this tutorial in this repo. You can go through this. Things like this, and this might scare you looking at something like that's not been updated from 2009. But in the Common Lisp world, this is common. You can use old libraries. Nothing would change. Nothing would be broken. This will work, and it does work. So if you're worried about the core drawing aspect, so there's a very simple getting started here. I just did this first, basically creating the objects that you need in the language of Cairo. So the surface, there is context, and then there is like, you need to move your pen and then select your color and then stroke and so on. Right? So the first thing I did was basically just copy this code and try it out and basically ensure that I have my drawing part working, right? I'm not going to show you that, but that's what I just did before I started thinking about even doing something with fractals, right? So you need your basics in place. So in this example, there is drawing to PDF, drawing to PostScript. There is also with this PNG. So this is what I've done. Okay. So let's look at the code. If you see here, this file is not too long. It's around 88 lines. But before I go into explaining this, let's take a step back and start out simple. So I'll just go back to my commit log and I'll go to the very first version. So this is the first version of the code, and you can see this is only 32 lines. So what are we doing here? What are the core things that are going on, right? So first we're going to define a package and import some other packages. So I'll get into more details here later. But we have already seen the CL Cairo 2 package that we imported, that we're talking about earlier, right? And now the rest of it is going to be in this package main. We start out with a simple grid. So a simple 2D array of hard-coded 100 cross 100 size with integers starting with 0 value, right? So this is just a very simple start. We can expand this grid later. And then the actual core logic of drawing is there in this function, where it's again taken from the file. So what are we doing? We are just going to take a loop over this 2D array and just going to draw each of these elements, right? So we're going to draw, what you see here is we're going to move to the pixel I comma j, and then we're going to draw a line to I plus 1, j plus 1, right? So this is a very dumb way to kind of simulate drawing a pixel. Not ideal, but Cairo doesn't have any other API, and this is the only way to do this, right? So here we also do one step in the middle to kind of get the color for that particular pixel. So in the starting, it is going to be just default values, right? We are not, we will worry about this later, but for now, the color is just a function which is going to return that just that pixel value. And now if you see the stroke function to do the actual stroke, and this render grid will do this render, right? But just to see at this point if it's all confusing, just to see this, just to have some kind of difference in the array, what I'm doing here is I just have this extra function which I'm going to compute, and the idea of this function is to simply set the diagonal values I comma j to 1. So basically for the diagonals, just like this example that was shown here, something similar to this, just to kind of like get your feet wet, I'm just going to set the diagonal elements of this grid to 1 and the remaining going to be 0, which means the color is going to be derived from as 0, 0, 0 RGB versus 1, 1, 1 RGB. Right, and so this is going to be a simple grid, and we just draw the grid, and doing this will give us confidence that we can go down and build stuff. Now let's try to run this file. So I'll open my Lisp REPL. So there are a few things we need to do here before we can get started. Because we are using these external packages, I need to quick load them. So that will also download them if they are not installed. But in this case, of course, I already have it installed. But it will load these libraries. Right? So once we have this, we are ready to run this, but I will still do a couple of more things here. The first is I will change the working directory to the current directory, essentially ensuring that the file gets created in this folder, right? The other thing I am now we are in a position, I think we can run this. So let's compile the whole file, and it's done some things. Now, because I believe the last command here is running the render grid, it should have already rendered. Let's see it. Yes, so there is the fractal source file, and then there is the compiled binary, and then there's the output PNG, right? So let's open this. So we see this diagonal line that I was talking about, just to ensure that we have something working here. Okay, so this is not great, obviously, because we only have 100 cross 100, so it's a bit pixelated. We can fix this down the line. Okay, so with that done, let's look at the next step, which is basically going and drawing the actual fractal, right? So let me again open the and check out this one. Okay, so now you'll see that we have something different here. We have a new function here to actually draw the fractal, right? Where is this logic coming from? In this Wikipedia page, there is a bunch of links and this page, which actually gives us a few different algorithms for being able to calculate and draw the fractal. So I really don't know the underlying math here. I am just going to copy this blindly. That's what I've done. I'm going to assume that this is correct and literally translate this into Common Lisp, right? And so there's a bunch of different algorithms here with different levels of optimization, but let's just start with the simple naive one. Let's not complicate things. Let's just start with this, right? So that's what I have done here. Now you must already be familiar with a lot of these things, but maybe I'll just call out a few interesting things. So one, for instance, is I've used the with clause. I don't think I showed this earlier on the video on loop, but the idea is this is the way you can start with some variables, the equivalent of setting some initial variables like int I equal to 0 in Common Lisp loop. And the other thing we've done here is we've used a while variant of the loop. So this is going to just evaluate this clause, and while this is true, it's going to do the rest of the block, right? And this is like a bit more traditional while loop, because you can see in this do block, we have this incrementation of the iteration variable. So iteration starts out with 0, and then we just keep incrementing it, and If when it reaches 1000, which is like the end condition, we definitely break out of this loop. So this is like a very traditional while loop implemented using the loop Common Lisp loop. There's one more thing here finally, which I just want to call out, and that is the finally clause, which is basically something that you can execute at the end of the loop iteration. So basically the last, when you're done, after this clause fails and the body can no longer be executed, then you finally go to the final block and run that code. So here we are explicitly returning the value of the iteration at this stage. Essentially this return call, the first time you see the return call, it's the loop is going to terminate and return the value, right? So this is basically earlier we have seen things like using do for side effect or collect to get a full list. This is the way you get a single item out of your loop block. So that's all there is to this. I don't think anything else has changed here. I think I have added normalization here because now we are going to set, according to the algorithm given there, we are going to set the value for each of those grid points, one of the iteration values. So that's going to be between 1 and 1000, and we're just going to scale it down to 1 because that's the Kairos API for setting RGB. This has to be between 0 and 1. Now, I think this kind of covers everything except maybe the array operations. We will come back to that, but let's look at this code run. So I'll have to compile this again. So I have to open this, but I just did. Control C, Control K will compile the old file, and because this last expression actually runs the render grid, and this one actually does the calculation. So both of that is done. By the way, if you want to look at the logic here, this portion, the three functions here, is actually responsible for calculating every point of the grid. This is the costly one. This is the one that will take time because right now we are still in an array of 100 elements, so it's small, so it kind of runs very fast. But if you increase it, you're going to have problems because if you see here, we are doing a loop I across the row and then j across the columns, but every pixel of the final image, we are doing this calculation and we are doing it serially here, right? As you can see, that's not, this is a kind of an example which can easily be parallelized. We will get to that in a moment, but for the moment it's serial, so it will take time if there is a larger number grid size. Okay, so I've already compiled this, so let's go and let's open this thing again, and you see our first fractal. It looks a bit fuzzy because it's just 100 cross 100 pixels, so that doesn't look clean, but that's something we can very easily fix by just increasing our pixel size. Switch back to the head comment. I think the rest of it should be explainable. Okay. So this file has more things here, but for instance, I have parameterized the size from 100 to something larger. So this makes it easier to redefine and so on. So let's take this version. Let's compile it first. There's a problem because we are importing the package lparallel now, and we don't actually have it. So let's do one thing. Let's quick load it as before. Okay. Okay, so it's compiled. Now, if you see, let's check the grid dimensions here. It's 1000 cross 1000, right? And we can run this version, the calculation in serial, the version you've already seen, right? This one. There is now also an optimized version. We will look at that bit later, but it's just one of these algorithms ported. So there is just done to see how long it takes. Let's take this function. It's still pointing to calc1, which is good. And let's run. So Mandelbrot calculate grid, and you see it's stuck. That's because it's taking time, because 1000 cross 1000 is a much bigger number. So as you can see, it's it's done. So not too bad, but you saw 10 seconds. We can go and see the output once, but the output won't be there yet because we only calculated the grid. We have not actually rendered it, right? So you need to run this also. So let me run this. Rendering is fast because it's just drawing, and let's open it now. And you see it's a lot more iris because it's 1000 pixels or 1000 pixels. Great, right? But you saw that it took a few seconds for this to run. We can even time this if you want. So we can just do like this, and this will give us some stats on how long it takes and how many instructions and so on. Still waiting. 10 seconds, I think, plus. Yeah, so it's taking 10 seconds. That's not great. We obviously can't scale up this. So this is where, because obviously the problem is very, very easy to parallelize, we will have now a parallel implementation, right? And so now there are different ways to do this. How do you do this? How do you do in parallel? So in this problem, it's very easy. You have to run the same function once for each pixel. So you can basically just spawn multiple threads and run each of them in parallel, right? Now, Lisp has a bunch of different libraries for parallelism. They do different things. They have overlapping features. It can be confusing. Now there is nothing wrong with any of them. So I guess for each situation you can pick one and use and so on. So in this case I used lparallel like you see here. I have also used other things like Kalispell or other such things, and we will cover those in other videos. But for today we are going to use lparallel. Now, so this is the package I'm talking about. There's some documentation. Here is another blog which is talking about how to use it. But the point of using this particular library for this exercise is that I don't want to spawn a thread for each of the grid pixels, right? That doesn't make sense. So I want a small number of worker threads, and I want to be able to add tasks that these worker threads are going to execute in parallel, right? So that's what we're doing here. So there's this line here where we create a kernel with a number of threads. So here we are saying that use 8 threads, and that's the number of workers that will be spawned. And then here we are creating a channel using make channel, and that is going to be used for the communication between here this main thread and those worker threads. So the API that they have provided is there's a submit task where you can just send a function. So in this case I'm just submitting on this channel the function that I want to call, which is just a lambda wrapper over the actual function. And here we're just setting the grid ij's value with the computation. So this expression will do the actual computation, and this expression will just set the value. Now you see here it's actually set to 2 right now. We can change this to 1 for the purpose of our comparison. And that's it. You submit the task, and in this case we actually don't really have any result on the task. We're not using any locks or anything because each of these element I comma j only one thread is going to access, so that's fine. And we finally just run this thing just to wait for all the results to come in. So this is just like waiting on a receive result will get some result back from the channel. There is no guarantee of order of what is running, but this is just to synchronize and just wait in this function for all the things to get finished. So because I changed this one, I'm going to recompile this, and because we did it time before, let's do it again, this time with the parallel version, and let's see how long that takes. And you see it's done in 1.8 seconds. So we have gone down from 10 seconds to around 2 seconds. Not bad. Now if you see here, there are only these two concepts: the kernel, the channel, and the task. But there are more primitives provided by this library or by other parallelism libraries, things like semaphores, mutexes, and so on. We'll see those in future videos as we need them. So in this case we have a very simple model, bunch of worker threads, a single channel where we can submit tasks, and they just get done in parallel by those threads. And I think one final thing to call out here is the optimized version. Again, nothing special. I have taken the code as it is from the Wikipedia page, where they have changed some operations and reduced some operations. So just for comparison, we can run the this optimized version both in serial and parallel. So let me compile this version. So we had this parallel, we had this serial version. I'm going to rerun the serial version. And last time it took 10 plus seconds. Let's see how long this optimized version takes. You see it takes around 8 seconds. So we have basically saved 2 seconds there because of the difference in the algorithm, number of operations. Let's also look at the parallel version just for completeness. Recompiled, and let's run the parallel version. Last time it took 1.8 seconds. It's taking 1.5 seconds this time. So basically, you can also see here that it's taking more than one core. It's in this case, it's 7.5 cores. That's because we have set the number of threads here to 8. We can try increasing this, and let's run this again. But I don't know if depends on the number of cores and number of hyperthreads that my actual hardware has. The final result is based on that. But you see there is an improvement, and you do see that from 7 cores you've gone to like 13 and a half, 14 cores, though we asked for 16 cores. Of course, there's going to be overhead because of the workers and all of that. But this is the general API. So there is one more thing I want to call out here before I end this video, and that is if you see this diagrams here, they do have a lot of logic for the color, essentially getting colorful diagrams out instead of just the black and white that we had, by using the iteration count and then coming up with some function for the color also. No, I haven't done that yet. This is something you can try, or this is something I might look into in a future video. So to recap, what we have seen today is we have around 90 lines of code where we are drawing fractals in two versions, one unoptimized and one optimized. And we are using the Cairo library to do the drawing pixel wise. Again, this is not the best library for this scenario. There might be a better option, but this is what I went with. We also have two versions of the calculation, one in serial. So this one runs everything in serial just for simplicity. And this one is the same thing, but runs in parallel using lparallel library.